Welcome back. If you've been with us through differential calculus, you've spent 15 episodes answering one question over and over. Given a function, what is its rate of change? That question has a name, the derivative, and by now you can compute it for basically anything. Polynomials, trig, exponentials, logs, compositions, products, quotients, implicit relations, inverses. The whole machine. Today we turn the arrow around. We ask the reverse question. Given a rate of change, what function produced it? That question opens the second half of calculus, integral calculus, and the answer turns out to be far richer than the forward problem. We'll meet the antiderivative, see why the answer always comes with a mysterious plus c, unpack the notation Leibniz invented for it, work through the standard table you'll use for the rest of your life, and finish with 3 full examples and a short history of how this all crystallized. Here's the new question. In differential calculus, you were handed a function capital F, say x cubed, and asked for its derivative. You computed capital F prime equals 3x squared. Now go the other way. Suppose I hand you the function f of x equals 3x squared and ask, what was the function whose derivative was this? You'd probably say x cubed, and you'd be right. Any function, capital F with capital F, prime of x equal to f of x, is called an antiderivative of f. That's the central object today. The forward problem, differentiation, is a recipe. Given any function built from elementary pieces, you can crank the rules and get the derivative. The reverse problem is genuinely different. It's a puzzle. Sometimes the answer is obvious, sometimes it takes work, and, as we'll see in later episodes, sometimes. For functions like sine of x squared or e to the minus x squared, no elementary antiderivative exists at all. For today, we stick to the cases where it does. But hold on, I said x cubed is an antiderivative of 3x squared. It's not the only one. Watch, differentiate x cubed plus 5. You get 3x squared. The 5 contributed 0 because the derivative of a constant is 0. Differentiate x cubed minus 1/2. Again, 3x squared. Same answer. Differentiate x cubed plus pi. Still 3x squared. Every function of the form x cubed plus c, where c is any real constant, is an antiderivative of 3x squared. There are infinitely many of them, and they form a one-parameter family. That's a permanent feature of antiderivatives, not a bug. If capital F is one antiderivative of f, then capital F plus c is another for every constant c. And the converse is true too. Any two antiderivatives of f on a connected interval differ by a constant. The proof is one line. If capital F prime of x equals capital G prime of x equals f of x, then the derivative of capital F minus capital G is 0 everywhere, and a function with 0 derivative on an interval is constant. So antiderivatives are unique up to a constant. The general antiderivative is capital F of x plus c, and you always have to write the plus c. Drop it and you've named one specific antiderivative, usually without realizing it. Picture. Take the simplest non-trivial case, f of x equals x. An antiderivative is x squared over 2. The general antiderivative is x squared over 2 plus c. Plot that for several values of c. You get a vertical stack of parabolas, each one shifted up or down from the next. They're all congruent. Geometrically, the family of antiderivatives is the original curve plus every possible vertical translation of it. Pick any x, say x equals 1. Look at the dashed vertical line at x equals 1. Every parabola in the family has the same slope at that point, namely 1. They have to because they're all antiderivatives of the same function. Shifting vertically doesn't change the slope. That picture is the geometric meaning of the plus c. You know the shape of the antiderivative, its slope at every point, but you don't know its vertical position. To pin down which parabola you're on, you need one extra piece of information, like the value of capital F at one point. That's the role of initial conditions in differential equations, by the way. Plus c is exactly the wiggle room initial conditions kill off. Time to talk notation. The collection of all antiderivatives of f has a name and a symbol. It's called the indefinite integral of f, written with this elongated s, the integral sign, followed by f of x followed by dx. Read aloud, it's the integral of f of x dx, and the whole thing equals capital F of x plus c, where capital F is any antiderivative of f and c is the constant of integration. 4 pieces. The integral sign is Leibniz's from 1675. He picked it because the integral was going to turn out to be a sum, an infinite sum of infinitesimal pieces, which he hadn't yet worked out the details of, and the elongated s stood for summa, Latin for sum. The function inside is called the integrand. The dx at the end serves 2 purposes. First, it tells you what the variable of integration is, useful when there are several letters floating around. Second, and this is more philosophical, it's the infinitesimal width that the integrand gets multiplied by, which will matter a lot when we get to the definite integral next episode. And the plus c at the end is the constant of integration, the wiggle room we just talked about. The whole symbol is one object, a family of functions, not a number. That word indefinite matters. The output of the integral of f of x dx is not a number, it's a family of functions. Compare with the definite integral, written with limits like the integral from a to b of f of x dx, whose output is a number. We meet that one next time. Quick contrast, because this trips students up forever. The integral sign gets used in two different ways. With limits on it, like the integral from a to b, it's the definite integral, and the output is a single number, usually interpreted as a signed area. Without limits, just the integral of f of x dx. It's the indefinite integral, and the output is a family of functions. Same symbol, two different objects, connected by a deep theorem we'll prove in episode 3, the fundamental theorem of calculus. For today, we only deal with the indefinite kind. No limits, no numbers, just families of functions and a plus c at the end of every line. First real rule. The power rule for derivatives says, the derivative of x to the n plus 1 is n plus 1 times x to the n. Run that backwards. An antiderivative of x to the n is x to the n plus 1 divided by n plus 1. Plus c. That's the power rule for antiderivatives, and it works for every real number n, except n equals minus 1, because then the formula tries to divide by 0, the exception. When n equals minus 1, you're integrating 1 over x. The antiderivative formula breaks down, but 1 over x does have an antiderivative. We know what it is. The derivative of the natural log of x is 1 over x for x greater than 0. What about x less than 0? Differentiate the natural log of negative x using the chain rule. You get 1 over negative x times negative 1, which is 1 over x. So the natural log of negative x is the antiderivative on the negative side. Combine both cases, the natural log of x for positive x, and the natural log of negative x for negative x, and you get the natural log of the absolute value of x. So the antiderivative of 1 over x is the natural log of the absolute value of x plus c. Memorize that exception. It comes up constantly. Second core rule. The integral is linear. That's a fancy word for two simple statements. First, the integral of a sum is the sum of the integrals. Second, constants pull out. The integral of c times f equals c times the integral of f. Put together, the integral of f plus bg equals a times the integral of f plus b times the integral of g. Why does this hold? It holds because differentiation is linear. The derivative of a sum is the sum of derivatives, and constants pull out of derivatives. So whatever antiderivative pairing works for f and g separately, you can add them or scale them, and the corresponding derivatives add and scale to match. Linearity is what lets you integrate a polynomial term by term, which is basically what we'll do in the first worked example in a moment. One footnote: when you add two indefinite integrals, the 2 plus c constants merge into a single plus c. You don't write plus c1 plus c2, it's still one undetermined real number. Here's the table you should memorize. It's just every standard derivative formula run backwards. Power rule reversed gives the first row, then the 1 over x exception. Then the exponential, the derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. That one is uniquely beautiful. E to the x is a fixed point of both differentiation and antidifferentiation. For a general exponential a to the x, where a is positive and not equal to 1, the derivative is a to the x times the natural log of a, so the antiderivative is a to the x, divided by the natural log of a. Then the trig block. Derivative of sine is cosine, so antiderivative of cosine is sine. Watch the sign on the next one. Derivative of cosine is minus sine, so antiderivative of sine is minus cosine. Be careful with that minus, it bites everyone. Derivative of tangent is secant squared, so antiderivative of secant squared is tangent. Derivative of cotangent is minus cosecant squared, so antiderivative of cosecant squared is minus cotangent. Derivative of secant is secant times tangent, so antiderivative of secant times tangent is secant. The last two are worth flagging because they look unfamiliar. The derivative of arctangent is 1 over 1 plus x squared, so the antiderivative of 1 over 1 plus x squared is arctangent of x. And the derivative of arcsine is 1 over the square root of 1 minus x squared, so the antiderivative of 1 over the square root of 1 minus x squared is arcsine of x. These two are how the inverse trig functions sneak into integral calculus. Burn this table into your retinas. Everything we do for the next 10 episodes runs through it. First worked example. Compute the integral of 3x squared plus 4x minus 5 dx. By linearity, this splits into three integrals, the integral of 3x squared plus the integral of 4x minus the integral of 5. Constants pull out, so it becomes 3 times the integral of x squared plus 4 times the integral of x minus 5 times the integral of 1. Apply the power rule to each. The integral of x squared is x cubed over 3. Multiply by 3 out front, the 3's cancel, you get x cubed. The integral of x is x squared over 2. Multiply by 4 out front, 4 over 2 is 2, you get 2x squared. The integral of 1, that's x to the 0, is x to the 1 over 1, just x. Multiply by 5 out front and keep the minus sign, you get minus 5x. Put it all together. X cubed plus 2x squared minus 5x plus c, because we always add plus c. Quick sanity check. Differentiate the answer. Derivative of x cubed is 3x squared. Derivative of 2x squared is 4x. Derivative of minus 5x is minus 5. Derivative of c is 0. Sum it. 3x squared plus 4x minus 5. Matches the integrand. Antidifferentiation is a puzzle, but you can always check the answer by differentiating, and you absolutely should. Every time. It's free. Second worked example. Compute the integral of sine x plus 2 over x dx. Linearity again. Split into the integral of sine x plus twice the integral of 1 over x. From the table, the integral of sine x is minus cosine x. Watch the sign, and the integral of 1 over x is the natural log of the absolute value of x. Combine. Minus cosine x plus 2 times the natural log of the absolute value of x plus c. Sanity check. Differentiate. Derivative of minus cosine is positive sine. Derivative of 2 times the natural log of the absolute value of x is 2 times 1 over x, which is 2 over x, so we get sine x plus 2 over x. Matches the integrand. Done. 2 things to flag here. First, the absolute value inside the log isn't decorative. It's what makes the answer valid on both sides of 0. Second, the minus sign on cosine. Students drop it constantly. Don't. Always check by differentiating. Third worked example. Compute the integral of e to the x minus 3 secant squared x dx. Linearity. Split into the integral of e to the x minus 3 times the integral of secant squared x. From the table, the integral of e to the x is the most satisfying integral in calculus. It's e to the x itself. The integral of secant squared x is tangent of x. Combine e to the x minus 3 tangent x plus c. Sanity check. Differentiate. Derivative of e to the x is e to the x. Derivative of minus 3 tangent x is minus 3 secant squared x. Derivative of c is 0. Sum e to the x minus 3 secant squared x. Matches. Notice the pattern across all 3 examples. Linearity to split. Table lookup to integrate each piece. Reassemble plus c. Differentiate to check. That's the entire algorithm for the kinds of integrals that submit to direct table lookup. The hard integrals, the ones requiring substitution or parts or partial fractions, come later in the series. For today, every problem you can crack is some arrangement of the table. One more caveat before history. Don't get the impression that every elementary function has an elementary antiderivative. It doesn't. Consider e to the minus x squared. That's the bell curve integrand, the Gaussian. Its antiderivative exists, has a name, the error function, and is studied extensively in statistics. But it cannot be written as a finite combination of polynomials, trig functions, exponentials, and logarithms. There is no elementary formula. The same is true of sine of x squared, whose antiderivative is called the Fresnel integral, used in optics and signal processing, and of sine of x over x, whose antiderivative is called the sine integral. Each of these is a perfectly well-defined function, but only as itself, not as an elementary combination. This is not a matter of nobody having figured it out yet. Joseph Liouville proved a theorem in the 1830s that precisely characterizes which elementary integrands have elementary antiderivatives, and these 3 fail his criterion. So the reverse derivative problem is honestly harder than the forward one. Differentiation always gives an elementary answer for an elementary input. Antidifferentiation doesn't. A brief history. 3 names. Newton, in 1666, working at Woolsthorpe Manor during the plague years, wrote a manuscript called De Analysi per Equationes Numero Terminorum Infinitus, on analysis by equations infinite in their number of terms. The manuscript circulated privately, wasn't printed until 1711, but in it Newton systematically computes what he called inverse fluxions, what we call antiderivatives. He uses them to find areas under curves. His notation was clunky, and almost no one outside his immediate circle used it. Then, on the continent in 1675, working independently and with no knowledge of what Newton had done, Gottfried Leibniz invented the notation we still use today. He coined the elongated s, the integral sign, for summa, sum. He coined dx for the infinitesimal increment. He published the differential calculus in the journal Acta Eruditorum in 1684 and the integral calculus in 1686, 2 short papers that gave Europe a working, writable calculus. The Newton-Leibniz priority dispute that followed is calculus's most famous feud. We covered it in episode 3 of the integral series, but the practical effect was clear. Continental Europe used Leibniz's notation, and 3 centuries later, so do we. The third figure is Cauchy. Through the 1820s, lecturing at the École Polytechnique in Paris, Augustin Louis Cauchy took the loose intuitive ideas Newton and Leibniz had been deploying, infinitesimals, vanishing quantities, ratios of nothings, and replaced them with the modern epsilon-delta definitions. Cauchy's cours d'analyse is where calculus finally became a rigorous subject. So roughly, Leibniz won the notation war, Newton and Leibniz share conceptual priority, and Cauchy made the whole thing stand up to modern scrutiny. where we landed. An antiderivative of f is any function capital F with capital F prime equal to f. It's never unique. If capital F works, capital F plus c works for every constant c, and that's the whole truth. Any two antiderivatives differ by a constant. The collection of all antiderivatives is the indefinite integral of f, written as the integral of f of x dx and equal to capital F of x plus c. The integral sign is Leibniz's, the dx is Leibniz's, and the plus c is non-negotiable. The power rule reverses to give x to the n plus 1 over n plus 1, valid for every real n except minus 1, where 1 over x integrates to the natural log of the absolute value of x. Integration is linear. The standard table is every derivative formula run backwards: trigonometric, exponential, log, inverse trig. We worked 3 examples: cold, a polynomial, a mix of sine and 1 over x, and a mix of exponential and secant squared. And everyone followed the same algorithm: linearity, table lookup, reassemble, plus c, differentiate to verify. We noted that the reverse problem is genuinely harder than the forward one. Some elementary integrands like e to the minus x squared and sine of x squared have no elementary antiderivative at all, a fact Liouville pinned down in the 1830s. And the history, Newton in 1666 wrote down antiderivatives systematically for the first time. Leibniz in the 1680s gave us the integral sign and the dx and published the working calculus in Acta Eruditorum. Cauchy in the 1820s made the whole thing rigorous. Next time we changed subjects: the definite integral, limits of Riemann sums, areas under curves, an actual number falling out at the end, no plus c in sight. And then, in episode 3, we connect the two stories, indefinite and definite, do the fundamental theorem of calculus, the single equation that says antidifferentiation and area finding are the same problem in disguise. Episode 2, Riemann sums and the definite integral. See you there. Antiderivatives are the doorway. Every integral you will ever compute, definite, improper, line, surface, contour, eventually reduces to signed a function whose derivative is this thing. That question is what the rest of integral calculus is about. Next episode, we leave the indefinite integral and meet the definite one, areas under curves computed as limits of Riemann sums with an actual number falling out at the end. After that, we tie the two stories together with the fundamental theorem of calculus, which proves that they were the same all along. If you want to ride the rest of integral calculus with us, subscribe. There's a lot of ground to cover. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.